Good afternoon, everyone, and welcome to C2QA's Fall 2022 Quantum Thursday series. We are so excited that you can join us on this afternoon. On the East Coast, it is 12 noon. Wherever you are, there may be different times at this point, but we are so happy that you took this next hour to join an exciting segment on C2QA and the work that we are doing in quantum information science. So this fall, we have been joined with a new moderator for this fall, that in Carl Clark. Carl is a senior educational programs representative working in the Office of Educational Programs at Brookhaven National Lab. And he has been here for a little bit over 3 years, working on behalf of stakeholder relations and doing different events and programs to try to join communities and ingratiate them into all that Brookhaven has to offer. Carl does have a background in science as well. He did his grad studies in atmospheric sciences, and he just loves, as he says, a good storm. So today, without further ado, we're going to turn over the meeting session to Carl Clark. I hope that you will welcome him with open arms. Carl, thank you for moderating today's series.
All right, thank you, Kim. Again, good afternoon, everyone. Good afternoon. This is a wonderful opportunity. This is a wonderful opportunity for you to hear from the Deputy Director of C2QA. But more importantly, this is an opportunity for all of you, students, undergrads, postdocs, early career professionals, the whole gambit, so that you are exposed to quantum informational science. This is an opportunity for us to build a strong network of diversity in quantum science, regardless of that definition of diversity. So we want you, as part of this conversation, and it is a conversation, for you to actively engage with our speaker, Kai-Mei Fu, who's going to be our first presenter this term. So let me just set a few ground rules, or a few, actually ground rules. Please ask questions. This is an opportunity for you to learn and be engaged and get further exposed to quantum informational science. Regardless of your background, regardless of your interest, there's a route for you, and there's a route for you to be a part of this network. We want you to feel like you belong within this quantum science initiative. This is the future. This is an initiative that is pushed by the White House. This is an initiative that is supported by the Department of Energy and its 17 national laboratories. So please engage fully with our presenter, Kai-Mei Fu. So I'm going to be doing a bit of introduction. After I do the introduction, I do want you to know that you can turn on your cameras if you want. We want to feel as comfortable as possible. We want you to place questions in the chat. I'll be monitoring that. Raise your hands. We'll also have opportunities for questions on the back end of the presentation. So Kai-Mei Fu is the Virginia and Prentice Bloedel Professor of Physics and Electrical and Computer Engineering at the University of Washington, and holds a dual appointment with the Pacific Northwest National Laboratory, Brookhaven's sister laboratory. Kai-Mei received their PhD in Applied Physics in 2007 from Stanford University. Their research focused on the synthesis, characterization, and control of optically active quantum defects in crystals, with applications in quantum networks and sensing. At UW, University of Washington, Kai-Mei is the director of UW's NSF National Research Training Program, Accelerating Quantum-Enabled Technologies, and the co-chair of the Interdisciplinary Quantum X Steering Committee. In Kai-Mei's free time, Kai-Mei enjoys spending time with their family outdoors in the beautiful, gorgeous Pacific Northwest. So without further ado, Kai-Mei, the floor is yours.
Thank you so much, Carl. As I'm beginning to share my screen, what I would very much like to invite people to do, if they're comfortable, is to share their video. this will actually help my presentation to you significantly if I have a few real faces to engage with. I don't mind if you're eating or you're drinking or you're pacing even. That's the beauty of Zoom. You can do what you want. I just love to see faces and have an interaction. Otherwise, this could just be a recorded video. The other thing that I want to recommend is to raise your hand or to put questions in the chat in real time. You guys are the folks that showed up to the seminar, which means you guys have the agency to ask questions and be the first people that get the knowledge out of this. So please ask questions throughout. So the title of today's talk is Quantum Point Defects for Quantum Networks. And this is a C2QA Quantum Thursday seminars. And this is a seminar that is geared towards students and beginning professionals in the area. I say this and it will try, but this is why I want you to ask questions, because sometimes I don't always succeed at meeting you where you're at now. I was asked to start by giving a little bit of information on my trajectory before I go into the research. And I also want to say questions on my trajectory and research, they're both open for questions, okay? So I grew up in Charlottesville, Virginia. I attended a public school in a small town outside of Charlottesville called Crozet, Virginia. And I took physics there. We were really fortunate to have physics offered there. Our physics professor took us to drag car races for field trips. So that's kind of our introduction to physics. I don't think he knew a lot more beyond mechanics and also car mechanics. So that was my introduction to the field. And at the time I thought I wanted to be a mathematician. I enjoyed physics, I enjoyed math. I went to Princeton wanting to major in math and found myself falling asleep at my textbook and found myself very much engaged in my physics laboratories. And so at that time I decided to switch my major and do physics. I really liked the hands-on part of physics and I liked using math for physics. That's turned out what I enjoyed. There were still moments where I didn't think I wanted to be a physics major. Like I said, I came from a rural school. I came to a very elite private university where students had a significant amount of more background than I did. And I felt that I wasn't doing very well. What was really helpful to me was I had someone who, after I worked my butt off and got an A-, which hadn't happened to me before, pulled me aside and said, no, you should stay in this field. You can do this. And that was a really nice moment in my life. And I'm like, all right, I'll learn a little more. And then I learned about quantum mechanics and then I was hooked. And that was the thing. You didn't learn about quantum mechanics in the first year then in physics. And so it was a little drier. Learned about quantum mechanics and I thought, wow, this is super neat. But I didn't know if I wanted to do graduate school. So I applied to graduate school, wasn't sure that whole, people were telling me 6 more years of school, not super convinced that's what I wanted to do. So I applied, I was accepted to schools and from the advice of my mother, I wasn't even going to apply. She's like, just apply, have your options. You can always defer. So I did that. I applied to grad school, I deferred, and then taught for a year in Singapore. And that was a fantastic experience. We had 72 vacation days on the job. Being a teacher can be nice. So I got to explore Southeast Asia. And about 6 months into that, I found myself in a bookstore because I had heard about a book that had just come out called The Introduction to Quantum Computing by Isaac Chung and Nielsen. All right, so I heard about this book and I found myself flipping through the pages and I'm like, well, I've never spent so much money on a book. This is the book I bought in Singapore. But I did, I was being paid well in Singapore. I bought this textbook, I started reading it, and someone saw it on my desk at my work. They said, you're reading this book. And they said, Isaac Chung is coming to the National University of Singapore as part of a workshop. And do you want to be invited to it? And I was like, sure, that's because someone saw this on my book. So I went, I've been reading the book. And what I did when I went to his talk was I asked questions. I had questions. I didn't understand things in this book, which was completely okay. I asked questions. I got to know him. And he said, you know what? You should study quantum information. This was back in 2000. And that kind of started this path down this road. He even suggested who I should study with. I was going to Stanford. He recommended his advisor, Yoshi Yamamoto. So I got my PhD in applied physics at Stanford University, doing quantum information. And I don't mention it on the slide, but I also had my first child. I got married and had my first child. So I'm living a life at the same time that I was getting my degree. I then did a postdoc at Hewlett-Packard Labs in the same field, which was across the street from Stanford. And this was really nice. And a really nice thing that happens in quantum information right now is that you can work in industry and government labs, getting significantly higher salaries than you would in an academic setting, which is fantastic because you still get to be exploring really cutting edge research. And this was fantastic for a couple reasons. One, as I mentioned, I had that kid in graduate school. I had a second kid as a postdoc, and my partner really wanted to do something very risky, start a company. So I was supporting him also at this time, all while getting to learn more about quantum information. So super exciting time in my life. I will say that it was a very busy time in my life. And then I became a professor at the University of Washington after completing my postdoc. And I had another child too. So just putting that in that life happens at all stages. While I've been a professor here at the University of Washington, this has led to many more opportunities, some of which you have heard in the wonderful bio that Carl mentioned at the start. Okay, so that's where I am now. This was my trajectory. Sometimes things seem like luck or chance, but it's not really that case. You know, I had gone to the bookstore, I was reading about quantum information, right? You see opportunities and you meet people and you ask questions and who knows where it might lead you. All right. So,
you have a question in the chat. It basically is ECE as in electrical engineering from Jacob Henry.
That is right. ECE is electrical and computer engineering. One thing that you may or may not notice from my trajectory is that I started as a physics major in a very theoretical physics department. In fact, I started coming to school thinking I wanted to be a mathematician. Then I got my PhD in applied physics, and now I have a joint appointment that includes an appointment in electrical and computer engineering. And this is not uncommon for people in physics to start to go more and more applied as time goes on. There's wonderful things about being fundamental and theoretical. There's also wonderful opportunities about getting more into applications and devices. And optics and photonics is really a field that bridges fundamental science and engineering. All right. So introduction to quantum networks and defects. So I am in the Pacific Northwest, and if you look up quantum communications, you'll find out that we have it all. In fact, we have internet at light speed from a company called Quantum Communications. That would be nice. Turns out quantum communication is not going to be super fast. It's not in the internet yet, but maybe one day it can be like what this classical communications company is hoping, that will have quantum communication. So what do I mean by creating a quantum network, a network that could be used for communication or computation? So this is a little less of a flashy image, but kind of distills the idea of a quantum network. Network is a graph. This is a graph of nodes and edges, or vertices and edges. These nodes correspond to a quantum bit. Unlike the classical bit, which is 0 and 1, these quantum bits are superpositions of 0 and 1. Long-term, they really need to be registers of quantum bits. So each one of these nodes is actually many, many, many qubits that creates a register, but it's okay for the sake of this talk to also just think of them as being one qubit that is that can be in the superposition state. And then these edges are signifying that there is quantum entanglement. There is some correlation between the values of 0 and 1 between two of these that can't be explained by classical methods. We need to use quantum mechanics to explain it, right? The applications for quantum networks roughly fall into two categories. One is communication, or the quantum internet, where we imagine that those edges are extremely long, enabling us to have secure communication, or even transmit quantum mechanical states of light. If we make those edges really short and put everything on a chip or a series of chips, then we can start thinking about this network for computation. And something that is sometimes not always appreciated is that creating a network like this and just doing single node measurements is equivalent to a universal quantum computer. So it actually can do everything that we think of as a gate-based quantum computer as well. So if we make these edges short, we could be connecting small quantum processors, but this entire thing can actually be a universal quantum processor as well. And there is a question. Yep.
Yeah, I was wondering, what is an ancilla? Sorry, I don't know very much about quantum.
That's an awful word to put in an intro talk. And ancilla is an extra qubit that you're using as a resource for something. So that's all ancilla means. It means it's not going to be the data qubit that stores the data, but you're using it maybe to do error correction or something else to preserve that data qubit. Yeah, and that will be used not too much in this talk, but that's the standard terminology for that.
Okay, thank you.
Great. Okay, so what exactly is that edge? We don't really want to be so fuzzy and say it's just something that has to do with non-classical correlations. If you like gates, this is what the gate looks like for creating the edge. So remember, we have these two qubits. They can be put in a superposition state of these two, and then we can perform this controlled gate operation. This is something called a controlled phase operation that essentially does nothing to the two qubits. This is qubit 1, this is qubit 2. If you multiply these out, you get 0, 0, 0, 1, 1, 0, and 1, 1. That's every possible state of this two qubit system. And what this control Z does is it just puts a minus sign if both of those states are in the one state. If you do this, that's you've created that edge. All right. If you like to look at the matrix representation, because that's how you think, then this is the matrix representation of it. And this type of two qubit state, we know it's two qubits because there's two in each one, is something called local unitary equivalent to an entangled Bell state. Bell states are these maximally entangled two qubit states, and local unitary equivalent is really fancy that says if I have this state, all I have to do is operations on B and operations on A alone. I don't need any more two qubit gates, and I can make it into a Bell state. Okay. So this means all I need to do is create a Bell state, and then I've created these edges. Okay. I'm not going to go through the math of this slide, but I want to stress from this that creating this Bell state or this edge does not require any local interactions. So every time we think of computing, we often think, oh, two things need to interact to create this gate. In these types of network schemes, we don't have to have things interact. What I'm going to show you is that what we do need is we need an extra level in the qubit. So here's qubit A, here's qubit B. We're drawing these lines to mean the different states they can be. These are energy levels as well. And the qubit states are these low-lying states, and they're connected at microwave frequencies. That's the energy difference between them is in the microwave domain. And then there's an excited state up here that couples to one of the levels. This excited state, which is just labeled as E, it gets excited by using a photon. So what we're saying here is we have our qubit states, and one of the qubits is accessible or could excite an actual photon. And this photon can then be transmitted, can go to a beam splitter where these two photons or these two paths can interfere. And on the click of the detector, we actually don't know which one emitted a photon. We don't know which one emitted a photon, which means we're left in the superposition of both of them having emitted a photon. And that means we end up being in an entangled state. All right. What you can see is that these are photons, these are flying qubits, which means this measurement here can happen in the middle. And this path can be arbitrarily long as you can get a photon to fly, right? And we can create this entanglement having never brought these qubits together spatially. All right, and then what is the node? All right, one more, oh, maybe not a question. So what is the node? This is something that theoretically could be any qubit node, any two-level system. You've heard about super exciting qubits. You've heard about trapped ions, maybe. You've heard about defects in crystals today. You'll hear about them. And even photons, if you could store them, they could be a node if you keep them still. We are interested in nodes that interact with light for this quantum network application. So we're not going to talk about superconducting qubits. Here is a circuit diagram of what we think about of a small quantum circuit. This is writing it as the graph state representation, kind of showing you that indeed it can be universal for quantum computing. And if we look at this node, the first thing that might be in your head is an atom. Atoms emit light, or trapped ions, okay? And in fact, atoms and ions are used as qubits in certain architectures. My research is the absence of an atom. So it turns out if you take a perfect crystal, such as diamond here, all these carbon atoms are actually in the diamond lattice structure. If you take out a carbon and put in nitrogen, for example, and leave one carbon nearest neighbor empty, you will get quantized energy levels and spin state levels that can mimic that three-level diagram that I showed before. So instead of having an atom stuck in vacuum, I'm taking out some atoms in a perfect periodic array of crystal to create this atom. All right. And this is the type of energy structure that I want to obtain that I showed you in the last slide for doing this protocol. In reality, the work is not so clean. You don't just get an atom that gives you these levels. And in fact, doing and understanding what happens in a single defect requires a significant amount of spectroscopy. This is the community's current understanding of this one defect in diamond, this nitrogen vacancy center in diamond, all the levels that occur. And then from this very complicated diagram, you want to isolate a three-level system to do your protocol. And that's a significant part of my research on the exploratory side is, can I take a defect? Can I understand why it has the properties it has? And then when I know these properties, can I back out something that is useful for quantum information applications? Right. There's another question.
Sorry. So for a three-level system, you have two levels that basically correspond to your 0 and your 1, or some combination of that. And then your third, like energized level, is how you send that information somewhere else. Is that how it's understood?
It can be understood like that. You are entangling this photon with this qubit when you send it off. And then when you measure the photon, you can cause there to be entanglement between two separate ones.
Got it. So the energy of that photon, because you have two different energy spacings, is how you almost encode that information when you send it off?
Not exactly. So I think we should punt this one to the end because it's a more advanced question. But in this case, it will actually be the presence or absence of that photon. It's called a dual rail scheme that's going to encode that information in this case. Okay, so there are lots of requirements for these defects that exist, and I'm listing a few of them here. That for you just to skim through. And there's even nice to have features. There are program managers and the government that says, you know what, and I'll say it too, I want this to operate at room temperature, or I would like this to operate at telecom frequency. So there's must-have features, there's nice-to-have features, and all of these types of properties are interesting to explore. The focus of the research that I'm doing in the C2QA right now is focusing on 3 of these, which is efficient photon collection, routing, and detection, and indistinguishable photons. One thing that I didn't mention was that in order for this beam splitter to erase the information about which defect emitted the photon, then these 2 photons have to be identical. They have to be spectrally identical, and that can be challenging. Right. Okay, so identical defects does imply identical photons. And by identical, I mean the spatial extent of the photon, the frequency, that energy of that photon, the time profile of the photon needs to be the same. And to 0th order defects are identical. If you look at one defect, nitrogen vacancy in diamond, and then 10 microns away, look at another one, they have the exact same structure. All right. And so this is a good starting point. To give you an idea of how rich this field is, you know, we have many different host crystals and many potential types of defects that exist. And they're all going to have different types of properties that depend on both the host crystal and the specific defect that occurred, right? So it's a good starting point that they're identical. And then there's the immense opportunity that we're actually in a solid state material that we can carve and create devices out of, right? What is its opportunity? One is we can capture the photon. In free space, the photon flies in every single direction. In solid state like diamond, it's even worse due to the laws of optics. A lot of the light gets trapped in the high index material already. So we can do this. We can make the defect emit all of its light in the same direction where you can collect it. You can alter the emission properties and frequency as well. For the nitrogen vacancy center, you see a photoluminescence spectra of the center where you're looking at the intensity of the light emitted as a function of wavelength, which is also a proxy for the energy. And what you can see is that only 3% of the light is actually in the transition that we can use for the protocol that I talked about. You can integrate this into a cavity. And here I just show you what different cavities look like. A small optical cavity that traps the light. And by doing that, you can actually make nearly 100% of the light emit into that range that you would like it to emit into. And then if you start looking at these type of devices, you can see that there's also the process for scalability. You can fit many of these devices onto the same chip, and you can connect these devices with photonic wires or waveguides in this case, right? So all of these types of opportunities require device integration with the caveat that you don't want to affect the intrinsic quantum properties of the defect itself. And this is a significant challenge in the field, is you want to integrate in a device and still preserve quantum information and still be able to, entangle that qubit with a flying photon with high fidelity. All right, so this moves me to the second part of my research, which is the creation and integration of diamond-based defects in devices. And there's kind of a subtitle for this, is where my research has been going, is minimally invasive photonics integration with quantum point defects. So this enhancement that I'm talking about to get more emission into the transition that you want, and also to have it spatially, this photon spatially emitted in the place you want, is something that was reported in 1950 by Purcell, and it's called the Purcell effect. And it basically says if you're able to trap light in a cavity, so this you can imagine just being two mirrors and the light bouncing back and forth, and this light is at the same frequency as the emitter that's in that cavity, then you can get an enhancement of the emission into that cavity mode, both in frequency and in space. This is called the Purcell effect. And the metric that you really want is the quality factor of that cavity, which is giving you a measure of how long that light can be stored in the cavity, and the mode volume, how small that cavity is. that can store, a single photon, for example. The reason why I'm talking about how small it is as a person, what this means in practice is that if you're making one of these cavities, you're going to be in a bunny suit in a clean room. You'll be designing them using electromagnetic software, and then you'll be bunnying up and learn how to use advanced semiconductor processing tools. All right, so this is a type of cavity. It's not two mirrors that are side by side like this, but this here is a whispering gallery mode cavity. And it is made out of gallium phosphide on diamond from my group. And in this cavity, what you have is, instead of having light interfere by bouncing between these two mirrors, the light interferes by, if it wraps around and is an integer number of wavelengths, you're going to get a cavity mode. So that's how it's total internal reflection. In this case, is one way to view this, this light trapping. And this is the actual mode that you observe. And this is these little green and red is done from electromagnetic simulation of the device structure. And then as the light propagates in this cavity, it can also couple to a waveguide and then go on to interact. In this type of device, we create the nitrogen vacancy center by implanting nitrogen into the diamond at a certain energy and then annealing to create the nitrogen vacancy center that can then interact with the evanescent field of this light cavity mode. And so we developed this hybrid geometry, this gallium phosphide on diamond, to allow us to independently optimize, not totally independently, but quasi-independently optimize the light layer and then the quantum defect device layer. Right? So why use gallium phosphide? It has a wide band gap, means it's not going to absorb visible photons. It has a high index, which means light can be trapped at the surface of diamond in gallium phosphide and guide it. And this high band gap and high index combination is not very common in materials. So if you're a material scientist and you're interested in problems, engineering, large band gap with large index is something that's challenging. We use gallium phosphide that's grown by molecular beam epitaxy because it needs to be very pure. And Qs of greater than 100,000 are possible with this transfer gap on oxide. And then gallium phosphide has additional features that I'm not going to get to talk about much today that we're leveraging for integrated photonics applications. And there's a question.
Hi, yeah. So do you implant your nitrogen first and then fabricate, or do you fabricate and then implant?
We implant first. We have to get the nicest nitrogen. In fact, we're doing silicon vacancy centers right now, but to get the nicest nitrogen vacancy centers or silicon vacancies, we actually anneal up to 1200 degrees Celsius. The gallium phosphide would not survive that.
Yeah, that makes sense. And then do you kind of just fabricate and hope that you're capturing some of these defects? Because I know that you don't really have a lot of say in where you implant. You can mask a little bit, but
you can actually mask quite a bit. We don't mask because that's not the outstanding challenge right now. We just over-implant and we get reasonable yields. Ideally, you would mask. We only need to get the defect within about 100 nanometers of where we want it. So doing an align. Yeah, so it's actually masking and implanting is not crazy. And that level of alignment is, of course, challenging. If you're a student, you're going to go in the bunny suit and do that in an academic clean room. It's going to be a fun challenge. It's not impossible, but then in an actual an actual fab, that's not crazy alignment.
Oh, wait, thank you.
Yeah. This is some examples, data from those devices from 2016 that I showed here, where you excite the nitrogen vacancy center and you collect and analyze the light that's emitted from the center over here, but you've actually enhanced it so it goes into this waveguide, and then you're collecting it all the way over here, right? And this is, and what you can see as we're tuning, I said the cavity resonance has to be on resonance with that energy transition. We're tuning this cavity resonance, and suddenly out of this grating coupler shoots this bright light. And that's the bright light from that single defect that we have in this cavity. But if you have a keen eye and you look at this bright light, you can see that its frequency is not still, it's wandering. And it's wandering because its environment is too noisy. and it's too noisy because of our fabrication processes. Okay, and there's a question.
Yeah, I want to ask, what do you think is the strengths of the this kind of nanodisk resonator compared with a photonic crystal resonator?
Yeah, so I love the nanodisk resonators because for a couple reasons, and those are on the scalability side. The advantage is the way to engineer the waveguide coupling to it precisely to outcouple and to connect more devices in a low loss manner. Also, I don't talk about this here, but your ability to tune and to have multiple like having free spectral ranges that are not insane. So you can actually get the cavity resonance more likely to be on resonance of your defect, and the fabrication tolerances as well. So if you look at silicon photonics and what's being done in silicon photonics today, there's not a lot of photonic crystal work. They're amazing devices, and I'm going to show you some devices that we're working on that we're excited about as well. But the long-term scaling and getting the fabrication and the alignment and everything where you need to be is more challenging. The advantage of photonic crystal cavities is that the interaction between that single defect, you get much smaller mode volumes, can be much larger. And so that's the huge advantage in this case. All right, so we had this problem and we did a lot of work to get defects that were the nitrogen vacancy center to be relatively well behaved about 100 nanometers from the surface. And these devices will not work very well with defects that are 100 nanometers from the surface. That's because the mode is trapped in this gallium phosphide and that diamond defect is just too far away. So we worked with a collaborator to say, all right, well, can we do integration in another way and maybe target an out of plane type geometry? So this is an example of what an out of plane geometry would look like, where you'd have your qubits. They're showing them in cavities here, but they would just be on your chip and they're emitting light straight up. And then you could entangle them in this type of optical multiplexer, for example. So these are the examples of optimizing defects. We did a study where we could optimize implanted defects in this way and get reasonable properties. They actually turn out on average not quite as good as native defects, but they're pretty good. And then we asked our collaborator, Alejandro Rodriguez at Princeton, how can we efficiently collect light from these? And what he does is inverse design. So actually designing, in this case, every single pixel in a device in order to optimize some objective function. And the objective function is collect light into our lens. So we get light from that defect. And then he can constrain it and say, all right, I know my NV is 100 nanometers from the surface. Kaimei says, I need a 1.5 micron footprint because she wants to put electrodes around it eventually in order to tune the actual frequency. And I cannot etch into the diamond because she knows etching into the diamond causes problems. And so this type of design is actually a huge blow up right now in the photonics field of being able to do inverse design. My main point of this graph is you get a lot of crazy things that come out that actually work. Like this is a wavelength divider for frequency. It looks kind of crazy, but here it's dividing out 3 different frequencies, right? And this is a nice review article on these types of methods. So Alejandro came back from this question and gave us this device here. And it was also constrained to our minimized fabricational feature sizes. And here you can see that we are able to faithfully reproduce this type of device. This is the gallium phosphide. This is the photoresist. This is the diamond surface. You can make tons of them, of course. And then you can confirm that you're coupled to a single quantum emitter, and you can measure the enhancement that you get of the photons that come straight out of this device. It was a 15-fold theoretically expected enhancement, and in our best optimal devices, we measured 14-fold experiment. So it was really good confirmation that this is working. However, when we went and probed the defects themselves, there was kind of a problem. So this is an example of an implanted NV center. It's wandering a bit. But after we fabricated this, having never etched into the diamond, but the diamond was exposed to a plasma, we got no signal at all from our defects. Our defects had gone quiet. And it turned out that the surface, the charge state on the surface had changed, and this had changed the charge state of our defect. We no longer had the negatively charged NV center. We could confirm this by doing a low temperature oxygen anneal. It couldn't be quite as high as we'd normally like, or else we'd damage the device. We could start to see the defect come alive again. but it maybe doesn't look that bad, except you see that I blew up the x-axis by a factor of 3. So it's worse than this, but 3 times worse than it looks. And it looks kind of noisy and blinky as well. And so what this has told us is that it was just, even though the defect is covered by this gallium phosphide in the middle, it's like centered underneath this little star-shaped feature, just the exposure to this chlorine plasma on the surface of diamond caused our quantum defect to not behave. And this kind of leads you to the dichotomy of these qubits. Not only are they information processors, they're also fantastic sensors. And that's a whole nother area of quantum information, is exploiting this sensitivity. But of course, we want to overcome this for quantum information applications. All right, there's a question.
Professor Fu, but I was curious if the chlorine, is there any indication that it was going into the matrix?
Well, we don't know. There's not an indication that it's going in very far, because we can actually see the normal type polishing marks that occurred after our oxygen index. Like, it's kind of we see the faint polishing marks. We see the diamond surface on an SEM looks exactly the same. So there's no roughening or anything like that. There's also no there's no visible on the 10 nanometer scale. There's no visible etching of the diamond itself.
Thank you.
There's another question.
On the previous slide, you had I think the zero photon line of the NV there, and then with the device. So you were able to get light there, but then when how is that different than the next slide where you said that you couldn't see the NVs?
So in this case, that's a really good question. So when we can see the NVs here, because we're exciting with green laser in this. When we try to do these measurements, these are actually a little bit different in that we're actually scanning a red laser over the resonance, and we're watching it light up. So these are super high resolution, and the defect has to be in the right charge state for this measurement to work. For this one, because you're exciting with such a high energy photon, you can give it a charge, happy enough for the measurement.
Awesome. Okay, thank you.
Yeah. Okay, so we kind of learned some things that I think are guiding principles. If you can at all times avoid diamond fabrication. It's not, there's some defects that are more resilient, and this is a challenge, right? Can we avoid diamond fabrication? We need to understand and control the surface. There are definitely people working on this. This is an outstanding challenge, but I'm not going to talk about that today. And we need to utilize different defects. So our next foray into this that I'm going to talk for about a couple more minutes, I do something an experimentalist should never do, which is change 2 variables in one go. So we are going to avoid all diamond fabrication, but we're also going to utilize a different defect, one that we know from talking to collaborators like Natalie De Leon, and also from the literature and from other research groups in this area, is let's use the silicon vacancy instead. So it's less perturbed by electric field fluctuations. And so in this next case, we're doing this forward design planar type thing. So this is utilizing photonic crystal type geometry. This is the theoretical work by the De Leon group, where we now have this beam of gallium phosphide, and under this beam will be the defect. So the defect has to be close. So we have to be within that 20 nanometers of the surface. And in this case, the light is propagating along here, and then we collect the light right at the edge of this waveguide through a grating type coupler device. So this is the next generation of devices. This is what they look like when they're fabricated. This is still on a silicon oxide chip. What we do is we actually transfer the gallium phosphide to silicon oxide, and then we do the measurements on silicon oxide of just how is this cavity behaving. And then based on that behavior, Srivatsa, who was really leading the fabrication on this process, what he did was he then tunes the frequency by etching the gallium phosphide on the oxide. And then this is stamped, this is taken off the oxide when it hits the right frequency, and then transferred to the diamond where we have these quantum defects, right? So this tuning, this is an example of being able to, you starting out with a resonance that's hanging out over here, and then you're ending up with a resonance that is hanging out over here in this case. And this is where we want to be before the transfer, and we know how that's going to shift when we transfer to diamond. And so this is
with the question.
oh, a question, great. Somehow I'm not.
Kimberly?
Yeah, I had a question. At what point do you abandon a material because the defect is maybe not working the way it should be?
I never want to say abandon completely. I think if you can't get the defect to work, sometimes you may need to shelve it. If you don't have an idea of how to probe why it's not working, that's why I don't want to say abandon. And that's why I want to say, like, when we talk about the NV center, there are definite challenges. We know it's sensitive to the surface. If you make a cleaner surface, then those challenges won't be such an issue. Making a clean surface in diamond, though, is a challenge. It requires a whole nother set of expertise to tackle that, right? So you may not focus on the NV Center for device integration in the time if there's other things that you want to tackle, but you may not want to completely abandon, or the community may not want to abandon it. You just need to be using a different tool to further advance that defect.
Thank you.
Or you would abandon it if you know fundamentally that's a problem. That's when you would abandon it. Like, fundamentally, there's nothing you can do to change that property, and you've proven it to yourself, then that would be a complete abandonment for the particular application.
Right. Okay.
So confirmation of defect coupling. So these devices were made, and we now excite with a laser in the center of the cavity and collecting light outside the gratings. Here you can tune the cavity mode, and then you can see that we can get coupling to these single SIV centers on resonance in this case. So this is very exciting for us. We do have PLE, but for time, I'm not going to share the photoluminescence excitation, the higher resolution scans. But what we can see is that this hybrid device geometry works. It can get reasonable coupling. The types of lifetime enhancements that we're observing, overall lifetime, which means emission into these cavities is being enhanced, corresponds to a cooperativity of about 2. That's where we are with these types of devices, even in this evanescent wavelength regime. Okay. So taking a step back, what I want to convince you is that quantum defects behave almost like atoms. It is very compelling because they're in a solid state environment. But some of the same features that lend themselves to scalability also present challenges that we have to confront. So it's wonderful that they're in a solid because we can create devices. It also means that the next thing closest to it is less than 3 nanometers. No, less than a nanometer away, right? The lattice spacing. And so you need materials. If you have a ppm sample just a few nanometers away, you could have a part per million. That's the total jargon. If you have defects at the part per million that aren't the defects that you want, just a few nanometers away from that quantum qubit may be a noisy defect, right? So this is a huge challenge for materials to either make that defect impervious to the noise or to clean the material up so that noise-inducing process is not there. Hybrid photonic platforms appear promising to minimize the disturbance of these qubits, which we can also call sensors for their environment. But this is just one strategy that quantum information scientists are having. For my own group, sorry, there's an extra thing in here, but what I want to stress is that there's many tools to address the challenge of homogeneity. If you're a theorist, it may be to develop protocols less sensitive to inhomogeneity. This is something that we've recently done in the field of sensing, wide field sensing, using the nitrogen vacancy center in Diamond, is have a new protocol that is less sensitive in this case to variations in strain. Another one is to use external electric fields to offset internal ones. So we know the NV center is unhappy because its electric field environment is changing. But as engineers, we can apply electric fields to offset that type of change. And so this is an example of doing this for nitrogen vacancy centers in the discrete-like resonance to stabilize a frequency that's wandering. This is a proof of principle. It's not stabilized to the level that you need for quantum information processing, but definitely we see a big change by applying these electric fields in the stability. And then finally, alter the photon properties after emission. You just have to trick the universe. The universe has to not know which defect emitted that photon. So convert those two NV center photons that are at 637 nanometers to telecom 1550 nanometers and shift the frequency a tiny bit of each one. So they're at the same telecom frequency. And then, I mean, that makes it sound easy. It's not, of course, that easy, but this concept is solid. You can combine frequency conversion and then erase the switch path information of where that photon came from. So that is another way, another trick that you can have to eliminate inhomogeneities. And then finally, the biggest parameter space, and this is my closing slide, is use a new defect. I loved Kim's question about, when do you abandon a defect? I don't like to abandon. I hate the word abandon. And I mentioned that if you know it's never ever going to work, of course you abandon it. If you're stuck, you do let it lie. You present the challenges. You hope through conversations the solution will come up. Maybe you're taking a shower. Maybe you have an idea, but you're not actively researching it anymore. You're letting it lie. Another reason is sometimes if you're working on something, there's an opportunity to work on something else that's more promising. Right? And that's where new defects comes in. And this is a giant parameter space. It's the material properties, the defects properties, and the functionality that you're trying to explore. And exploring this space is immensely challenging, but also should be immensely rewarding if it's explored in the right way. Yes, there's a question.
Thank you for a nice talk. I'm still trying to understand those three states that you shown in the beginning. The ground state 0, 1, and the excited state. For an atomic defect in a material, is that corresponds to valence band, conduction band, and a defect state defect level, or?
No, usually all of these levels are inside the band gap. They're all inside. So this would be, the ground state is typically the spin level of an electron defect state. All right. And then the excited state is exciting to an orbital, a bound orbital of the defect. So ideally, you don't want any of these levels to actually be overlapping with the valence or conduction bands. You want them all inside the band gap. There's another question.
Thank you.
I think that is me. I wanted to ask whether or not, when you say efficient photon collection and routing, do you use multi-layer gratings?
Sorry, can you
do you
repeat
use multi-layer gratings or single-layer grading in terms of improving the efficiency of photon collection?
Yes. So right now we are focused just on collecting into the waveguide. We use for our gratings, we actually use some ML techniques to optimize these grading structures to emit light somewhat efficiently. It's a single layer. Our grading efficiencies are like 20 to 30%. They're not at the 100% level. Long term, we do this because we look at lots of devices. We make hundreds of devices. We can do this from the normal mode. Long term, I think you need to be going side coupling, for example, or wiring directly into fibers, doing photonic wire bonding.
All right, thank you.
There's something very important that I do have to put up. I said that was my last slide. There's actually 2 more slides. This slide's really important. The acknowledgement slides. I obviously didn't do all this work. I get to just talk about all this work. The people that are doing this work are the students and the postdocs in my group, and we focused on the Diamond team in this talk today. The collaborators that I work with, I am not a materials grower. So all the materials that you see is coming from a wonderful collaborator in this case, and everyone that you see is eating and living. So they are all being supported by the various funding agencies that support this work. And the highlight of today's talk was really supported, this hybrid integration for single defects was supported by the C2QA. And then what I like to leave this up when I get questions, because you can see absolutely how amazing it is in the Pacific Northwest at the University of Washington, and to entice you to come in person to visit us. So I think we have time for a few more questions now that I've made it through my real last slide.
Okay, so we do have questions. So if you have any questions, please place them in the chat, raise your hands, or unmute yourselves. All right, China?
Yeah, I have a little question about still the 3-level system. So how can you read out the 1 level since you do not have anything coupled to it? I mean, optically coupled to it.
Yeah, so the way, so you're saying, all right, well, how do I read out this level, right?
Yes,
So
yes.
if you're reading out this, if you apply a resonant laser to this transition, it's a cycling transition. So if you're doing readout, you're not actually, ignore this part. You've already entangled, but maybe you want to know, you want to do a readout mechanism of this qubit after you've done the entanglement. This is a cycling transition that you would resonantly excite that would emit a lot of photons. All right. So if I apply this laser and I get a lot of photons out, I know that I was in the 0 state. If I don't get any photons out, I know I'm in the 1 state. And so you usually give a threshold. You say, all right, as soon as I detect 10 photons, that's my threshold. I know I was in the 0 state.
Okay. Okay, so basically you still need an ensemble to do it because you need a lot of photons.
No, it's single. This is a cycling transition. So when I excite this state, it's going to decay back to this. So you need something called the cycling transition. So you can do this many times and you can do single shot readout.
Okay, but then what if your photon is just lost somewhere? You know, then.
All right, so what you're asking is, how do I read out the qubit state? When you do this protocol that you're seeing here, you don't read the qubit state out. You don't ever want to know which one emitted the photon. When you would do the readout would be after you're entangled and you want to do a measurement. So this is a protocol where you get a photon, you know you got a photon because one of these clicked. If it didn't click, it failed. You do it again. If you get a click, you know you got a photon. All right.
Okay, so here is just nothing to do with the 1 level for now, I guess.
Yeah, so later you do need in all these protocols the ability to read out the qubit at the end, and that's done by exciting many, many times.
Okay, cool. Another thing is I'm not very familiar with the MV system, so I guess the 0 and 1 is split via some magnetic field, some Zeeman split, and why the excited state is not split up.
Okay, so these are excellent questions. First of all, 0 and 1, actually, it's a spin triplet state. One of these is the ms equals 0 state, and one is usually the ms equals +1 or the ms equals -1 state. In the spin triplet state, this is actually split at 0 field by 2.8 gigahertz, 2.9 gigahertz. So you don't need a magnetic field in the ground state. The other question, but you asked, why isn't the excited state split up? Actually, there's tons of levels. So here you can see there's actually 2 levels here. They made it fat. So this is the +-1 state. This is without magnetic field. Here you can see there's many excited levels, but you can decouple some of these levels from your system. So you're making an effective Hamiltonian. You're creating and just bridging these transitions from this more complicated energy level structure.
I see. Cool.
And it's never 100%. There's always problems, and that's part of the challenge. But there are usually clever things you can do to achieve your goal.
I see. Thanks so much, and thanks so much for the wonderful talk.
You're welcome.
And Jaime, I do agree. Thank you so much for this wonderful talk. The recording will definitely be available on the news and events page of the C2QA's website. So if there's any additional questions, you can always reach out to Jaime, but please note this recording will be placed there. So Jaime, thank you so much for the talk and this great presentation.
All right, thank you. It was my pleasure to be here.
Thank you.
And before we let you go, I do want to quickly say this, that the C2QA Quantum Thursday is a conversation. So we do appreciate the conversation that took place today. This is the 4th iteration of Quantum Thursday. So We hope that as you continue to attend these presentations, you get an idea, a better understanding of quantum informational science and the direction and the work that's going on in this field. With that said, thank you all, and we do hope to see you at our next Quantum Thursday, 2 weeks from now. So take care, everyone.
Thank you, everyone.
Thank you.